Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I want to introduce you Sylvie Aubry. So Sylvie received her PhD from in Paris, in France, from University Pierre and Marie Curie. She's currently a research associate at Stanford, and she has been involved with Sandia National Labs since 2006 or 7?
So Sandia was 2001,
2001, sorry.
2006.
Yeah. So she will today she will share. So I was thinking it would be a good presentation, and she will share his experience with tuning and optimizing numeric algorithms, but from an application perspective. So.
Thank you.
Thank you.
Okay, so as Laurent said, I'm gonna talk today about what I've been doing since my PhD. Well, during my PhD, then during my postdoc, then during my stay at Sandia National Lab, and hopefully, so I will cover several topics. So I may go a bit fast between one topic to the other, and please stop me if it's not clear or too fast. All right, so the general topic is numerical algorithm applied to material science problems. Okay, so here is what I'm gonna talk about. So I'm going to introduce something called sequential laminates. These are the algorithmic tools that I'm going to use. And I'm going to apply this algorithm to two important problems. One is topological optimization, and the other one is two solid mechanics related problems. One is for shape memory alloys, and another one is for plasticity and metals. And then I'm going to talk a little bit about some parallel algorithms that are in LAMMPS, which is a big, massively parallel code, and ParaDiS. So the way it's set up is a little bit chronological. I've done topological optimization during my PhD. And during my postdoc, I applied the method that I learned during my PhD to kind of material science, solid mechanics application, these two ones. And then when I moved to Sandia and then to Stanford, I kind of switched a little bit my work to using parallel code and implemented parallel algorithms in them. All right. So let's first talk about topological optimization. So what is it? Well, you have what you want to do is find a structure that has some good properties. For instance, here we are interested in the design of mechanical parts for application in civil engineering, car makers, aeronautics, aerospace. And the idea is to to do trial and error techniques, which are expensive and which are an imperfect way of optimizing a mechanical part. So what I've been doing is to use optimization techniques to maximize a part of a structure. For example, with some objective function, like you have a given weight, you want to have the most rigid structure, you have the most resistant structure, the less expensive one, things like that, some objective function. And the idea is to develop algorithms to compute these optimal shapes and structures. So, okay, and the two examples that I have here is, for example, part of a car is a car suspension triangle in two different cars. So that was done in France, so these are French cars. Okay. So, okay, what is topological optimization? Okay, so we have a domain, and we have certain loading condition on the domain. And the idea is that the problem is the following. You have a certain weight of material that you want to put in your domain, such that the material is the most resistant to this loading configuration. Okay, and so what is the answer to that question? Well, we have a mathematical theorem, so a rigorous proof that shows that the optimal shape for a given structure is this shape, which is a composite shape. So here, everything that is black is material, everything that is everything that is white is void, and everything that is gray is a mixture of material and void. And so we have shown that this is the optimal shape of such a loading condition and a given weight. And what's interesting here is that in each material point in your domain, you can define precisely the microstructure, and the microstructure is a laminate, and I'll explain that a little bit. Now, if you give that to a car maker, for example, you say, okay, this is the optimal shape, he won't be able to construct it. So we have some kind of post-processing step that's going to give you the optimal shape, like as a black and white material void shape. But what's important here is that because we have this optimal structure, we can get all the different details here for an approximate shape of your structure. And all these details are given because you have the optimal shape. So how does it work? So this is here a little bit of mathematics. So we want to find the structure, for instance. So you have to define some kind of objective function. Here, the objective function is to maximize the resistance of a mechanical part, for instance. And you have the weight. So that can be mathematically formulated as this equation. Okay, so let me explain this equation. So here, that part is what is called the compliance, is the resistance of your shape. And this chi function here is so here on that form, it represents the weight. And if you put it on this form, it's some kind of, you maximize the resistance for the given weight, and L is just a Lagrange multiplier here. So what's important here is these two infimum. So you minimize over the stress in your solid. So when you have forces that are applied to your solid, you have a stress inside your structure, and you have to minimize the stress. Of course, the stress depends on the material. So it depends on each point of your system. And you have another infimum here, which is, so that's this material or void characteristic. So when chi equals to 0, it's void. And when chi equals to 1, it's the material A. All right. So that defines kind of the problem. And if you want to solve that mathematically, find the optimal shape of your structure, well, you can't, because there is no solution. Why isn't there any solution? Well, because your problem is too restrictive in a sense. You have like a black and white solution there. And you can show rigorously that you can transform this problem into one that has a solution. And the process to do that is called relaxation. And so what you do during this relaxation step is that you replace these two infimum by, instead of minimizing over this chi function, you minimize now over a proportion, theta, that is a value between the whole interval 0, 1, instead of just 0 and 1, okay? And you minimize also over all the possible shape that you can construct with the material A and void in proportion theta and 1 minus theta, okay? And, okay, the problem is that this larger class of composite that you define is unknown. Nobody knows what it is. It's too complex and too varied. So there is, this is where we are saved in a way. There is a special microstructure that is called sequential laminates. And the way you construct such a microstructure is that you have here gray, gray, and let's say all black in a given direction. So that will be a laminate of rank 1. And then you can, in the black area, you just you give yourself another direction and a given proportion, and you put black and white again. So this is how you calculate a sequential laminate. You give yourself a direction and a proportion of lamination, and with that you can define several rank laminates. And it happens that these sequential laminates are actually optimal for that problem. So you can find there is a rank 3 laminate that achieve the minimum in the minimization problem. And so with that, you can define a numerical algorithm to calculate your optimal shape. So the way it works is the following. You have a minimum over, over the shape. So now the shape is given by the proportion theta and the laminate, AL, which is a function of theta, that you know analytically as a function of theta. And so you start by minimizing. So you start with the initial shape. Then you minimize the stress given the external loading condition. And then you iterate like that until your algorithm converges. And once it converges, you get this kind of shape. And then you have this post-processing shape that I was talking about, where you transform this optimal shape into this material void-only structure. And the way you do that is that you play with that proportion theta. For instance, if theta is greater than 0.5, you say it's going to be material. If theta is lower than 0.5, you're going to have void. And again, you iterate like that, and you get some kind of not optimal, but close to optimal structure. So what you can do with that, okay, so there are several properties of the algorithm. One, it doesn't depend on the initial shape, because you have an analytical expression for your algorithm. So here, for example, you start with a material that is completely, that fills entirely the space, and you get a given shape. And that's an example, for example, of this transmission tower where the optimal design of a metallic part for a given resistance, for a given loading condition. Okay, and so the good thing also is that you have a certain flexibility in choosing the objective function. And I have done a few different objective functions. One is that you can extend the loading condition to several loading conditions. So now that's the same transmission tower, but you change the loading condition. You have to have resistance for 2 given loading. And this is an objective function where, for MEMS application, where now you have a function of the displacement inside the objective function. So that's kind of what I wanted to say about topologic optimization. And now let's move on to constitutive equations for mechanics. So here, okay, maybe I should show the picture first. So you have, in shape memory alloys, laminates have been observed. So those are actually, those are laminated microstructures that have been observed in nature or in laboratory, where you have, so the way it works is the following. You have what is called a shape memory alloy, and here it's nickel, copper, aluminum, and it has an austenitic phase, which is mainly a uniform deformation gradient, and it can have a martensitic phase with different variants. For instance, nickel, copper, aluminum has 6 different variants. So these 6 different arrangements of laminates. So here you can see the boundary between an austenitic phase and a martensitic phase, which is like here, just a rank 1 laminate. And here, a rank 2 laminate. So you have two different orientation there. So we want to model that. So let me go back to my slides here. Yeah. And so we can use the sequential laminate tree to model these microstructures. And also, I'll show after that we can model other microstructures as well. Okay, so let me tell you a little bit about shape memory alloys. So the shape memory alloys go from one phase, one variant to the other by, you have to change either the external stress or the temperature. If you do that, you can go from one martensitic phase to another. And in nickel, copper, aluminum, as I was saying, you can have phase transition between the austenitic phase and different martensitic phase. Okay? So if you model the problem now mathematically, you want to minimize, you have an energy that is, so each variant in your martensitic phase is a convex function, is some kind of, here in 2D, it will be like that, some kind of function. So in 3D is an energy well. And you have like several of them, you have m of them. So for example, nickel, copper, aluminum, you have 6 of them. And you want to calculate the energy, you want to minimize the energy of your system again. And the minimization, for example, here of that kind of energy, it will be given by that. The problem here again is that we cannot calculate this relaxation. It's too complicated because there is no explicit formula for them. And so what we do is the next best thing. We say, okay, we cannot solve that problem, so we're going to solve an approximate problem, knowing that in reality we observe this laminate, so we shouldn't be too far from the real solution. And the laminate, in a sense, is instead of solving that problem, you solve some other problem. You solve some approximate problem, for example, like that. And so here now, you replace that formula again. So using laminates, you can define another energy, which is going to be close to the one you want to solve. And the way it works at the microscopic level, again, is the following. You have your gradient of deformation f for a given little space in your system, and you replace it by a rank 1 laminate, which is going to be defined by, instead of f, you define f plus and f minus. And f plus and f minus are going to be defined such that you have a direction of lamination and you have a proportion. So it's a bit, there are similar ideas that with topological optimization. And you can represent this rank 1 laminate by a tree and a tree structure. So you have your f, your deformation gradient, that is now replaced by f plus and f minus. And f plus and f minus are defined by this relation. They are defined using f, but you also have these 3 parameters, so lambda, a, and n, which are going to define your laminate. Lambda is the proportion of lamination, n is the direction, and a is so that there is no jump at the boundary. So if you do that, well, you can do something a bit more complicated. Now, let's say you want to find the minimum structure. So how about like replace now f minus by 2 other f's, 2 other deformation gradient, f minus plus and n minus minus, with 2 other proportions, and you have a set of other parameters. So, and then maybe this structure will minimize the energy even better. So from these deformation gradients, all these f's that you get, you can define another energy. Well, so that's an energy which is given by the following. So now you have a sum over all the different energy wells. And what you do is that you have to minimize over all the lambda, a, and n that belong to your tree, the interior node of your tree, and over all the different variants, oh, that should be a capital M here, all the different variants of your martensitic phase. And so we've done that. That was the goal. All right. So in your tree, you have to have equilibrium relation. And these equilibrium relations are some mechanical meaning. So you have to have some kind of equilibrium relation for the ends, for the A, and then for the lambdas. And these equilibrium relations are actually like traction equilibrium, torque equilibrium, and force equilibrium. So this has to be satisfied by our tree structure. Okay, so here is the algorithm. So as you can imagine, this tree can be defined recursively. So you have a F, and you can define 2 leaves, and then with 1 you can define 2 others. So that there is a recursive relation in laminates that is based on the definition. So the way it works is the following. So you discretize the 2 time steps. And so the first time step is that you have a deformation gradient F, and you calculate this F plus and F minus, and then you calculate and the energy of the new energy of F, which is a linear combination of the energy of F plus and F minus, and you look if that new energy is lower than your initial energy, and if it is, then you start to create 2 leaves, all right? And so then you iterate on that. So you have a tree which has that many whatever leaves and interior nodes. And the first phase is to equilibrate the tree. So we have here to minimize over all A, lambda, and N that belong to the tree. So we use a sequential quadratic programming algorithm to do that. So once the tree is equilibrated, then we start the evolution of the tree. So first is pruning. So if during the equilibration you have a lambda that is close to 0 on 1, this is a null subtree, so you have to remove it. So that's pruning of the tree. And you can have branching. So for all the different leaves that are not interior node, you have you try to create new leaves based on that criterion over there to minimize globally your energy. And there is also, again, it's kind of a post-processing step. So you have your tree, your optimal tree, and you want to make sure that it doesn't continue like infinitely. And one way to do that is that there is a length scale associated to each laminate, the whole tree, and that tells you where to stop your tree. So we've done that. We've calculated that. We've implemented that. And we applied it to indentation simulations. So here we have a finite element mesh. So you have a block of material, and you create points in this material. We're going to be material point where you're going to apply this energy in each point, and you find the minimum energy for each point here on that mesh. And we have an indenter that is going to press over the material and to measure the response of the material to that indenter. And the numerical model that we've developed is going to predict the microstructure and the deformation of the material here. So we've done that, and here I'm showing some of the rank. So here they are like mainly rank 1 or rank 2 laminates that appears during the minimization procedure. And here I'm showing curves for the energy and the force. So if you don't do anything, you have the red curve. And we try several strategies to minimize the energy, but globally our algorithm is going to minimize the energy and gives you an optimal structure. All right. Now we have applied the same algorithm with a bit different ideas on lamellar microstructure that are observed in large deformation. So some experiments have been done at Sandia National Lab by Darcy Hughes, where she observes these lamellar microstructures when she does cold rolling experiments. So what you do is that you really you roll the material to have this different structure. So you start with the material that has large grains, then you get deformed, elongated grains, and then you get really small grains. And they are very, very highly deformed. And so so the idea here was to validate our algorithm and show that we can predict microstructures. So here that's just one of the results that we have, where we were able to show that the stress, if you apply a certain strain, the average angle that is part of these layers is very well captured by our algorithm. All right, so this is all I wanted to say about this lamellar microstructure. Let me talk a little bit about the two parallel codes that I'm working on right now. The first one is called LAMMPS. And so the idea here is to model heat conduction in solids. Okay, so yes?
Do metals conduct heat?
So
phonons?
it's semiconductors.
Oh,
Semiconductors. Did I put metal? So metals, it's phonon and electrons, right? Yes. So here it's mainly, this was done for semiconductors, silicon. So here the idea is to calculate how a material, so here you have your material, and you want to know how material geometry are going to block or not your thermal transport. So the way it works is that what I've been doing, so it's pretty recent work here. So what we have developed two methods. One is the direct heat flux method, and another one is a phonon-based method to model thermal transport in this structure and calculate the thermal boundary resistance of this material geometry. And to do that, we need to model all the atoms in the structure, which can be pretty big. We've done some simulation that, okay, there are two things. First, we have to model for a very large number of atoms because we want to do bulk material, so it has to be pretty big. And also, okay, there are periodic boundary conditions, but still, you don't want your result to be dependent on your system. And also, we have to do it for a very long period of time because, especially with the direct heat flux method, we want to make sure that we have a result that doesn't depend on the time we use. So here, there is a need for a massively parallel code, and this is LAMMPS. So what LAMMPS does is it calculates basically molecular dynamics, which is you have all the atoms in your system, and you have to model the interactions between the atoms and the force of the atoms. Okay, and so what is LAMMPS? Well, LAMMPS, it's mainly a spatial decomposition algorithm where you partition your domain of atoms. And 3 different algorithms have been implemented in LAMMPS. And they are good and bad for certain applications. There is atom decomposition, there is a force decomposition, and there is the spatial decomposition. We mainly use the spatial decomposition. And so what we've done in LAMMPS is that we've implemented this heat flux method. So the way it works is the following. You have hot region where you add some energy to the system. You have a cold region when you remove energy in your system. And you have a heat flux that goes that circulates here. And so you iterate. You have a certain potential for, here it's silicon, so a certain potential for silicon. And here in the middle, at z equals 0, you have a grain boundary, for instance. Here it's called a sigma 2901 grain boundary. And we want to know how much this energy scatter and reflect energy. So from this direct heat flux method, you can get a temperature profile that is this. So here it's the temperature in your system as a function of z Z is that direction. And here you see you have a gradient of temperature due to the grain boundary. And from this gradient of temperature, you can calculate a quantity that is called the Kapitsa conductance that is going to tell you how much your energy conduct, how much your grain boundary conduct energy. Okay, and we also have done another method, which is called lattice dynamics method. So again, that's implemented fully in LAMMPS. So here the idea is that you have a phonon that is modeled as a Gaussian wave packet, and you give it an initial displacement and velocity given by dispersion relation, and you can calculate how much this phonon is going to transmit and reflect energy when it goes to across the grain boundary. So let me show you. I think the movie started, but I'll show you. Hopefully this is going to work. Yeah. So you see the phonon starts, and here it hits the grain boundary. Some of it is reflected, some of it is transmitted, some of it is reflected. And you can do that with different phonon that hits the boundary with different angle. And if you do all this simulation, and that's actually pretty expensive simulation, you can get this kind of curve, which is the Kapitsa conductance as a function of temperature. And as you see here, we get so at the temperature limit, we get like 0.7 something gigawatt per meter square Kelvin. And that's very similar to, okay, that's very similar, oh, now we want to run the movie, to what we were getting, okay, with the other method, which was 0.8. Okay, I guess you're going to see the movie again because it doesn't let me do anything else. All right. Okay, so now ParaDiS. So here, the idea, it's another parallel code, another one. And the idea here is to model the strength of material by modeling the dynamics of dislocations. So here it's metals. So here, okay, here that's an example of millions and millions of dislocations that are like in the simulation box. And you see the white here is the junction. And actually that's an interesting problem because they have shown here that you have triple junctions, and this was new. That had been never observed in simulations, and they were able to do that because that is this triple junction work. I wasn't part of it, but the good thing is that they were able to observe triple junction that had not been before seen in a simulation program, and they were able to see that in experiments. So how does this one work? Well, so this is a very complicated code because you have the following issues. So you have a dislocation. Dislocation is a set of nodes and segments. And you have some external force or displacement or stress applied to your system. And you have to deal with millions of dislocation that moves and interact. So they interact between each other, and they also interact to the external stress. So that's actually a very complicated problem. And it has been parallelized using spatial decomposition. And there is also a dynamic load balancing there because dislocation tend to cluster in some region of the domain. And here, the code is able to do topological changes. For instance, here you can insert a node, or if you have two nodes that are connected to the same segments, you reduce it in one segment. And the impressive things here is that this code has been shown to be scalable on a 132,000 processor on Blue Gmail. And what's also interesting is that, okay, the movie again. So you can get the dislocation density, and as you can see, it increases with strain, and you can get strain-stress relation, and this gives you the strength of your material. And so the novelty of that code is that before, you could just go up to here. And because it has been done in such a way that now you can go up to here. And you are able to observe something very important in strength of metals, which is strain hardening. So this was proven to be really successful code. All right. So okay, I arrive to my conclusion. So I hope I convinced you that mathematical and numerical methods can be useful to solve some important application in material science and solid mechanics. And so what I've shown is that you have parallel capabilities and efficient algorithms that are essential to solve these problems. And the problems that I've shown are structural optimization, constitutive equations, or material response for shape memory alloys and plasticity, thermal transport in semiconductors, and strength of metal. Okay, thank you for your attention. Yes?
What is the spatial decomposition you're using?
In which one?
In the last work for parallelizing on the blue gene?
So the parallel decomposition is standard parallel decomposition. What is important here is the load balancing.
So it's a regular grid?
Yes, it's a regular grid, but then there is this load balancing. So there is a calculation of how much each computer spend time, and according to that, you have decomposition of your space. So it's not regular. It starts regular and then it goes non-regular because there is this dynamic load balancing issue.
So what kind of data structure is it? Once you re-partition, what kind of data structure?
Well, it can be very, is there a pen here? It can be very different. You can have like a region where you have a very small processor, very small processor domain, and region where you have a very large processor domain.
Is it a hierarchy or just a decomposition?
It's a decomposition.
No hierarchy.
No. Yes?
Since you can do strain hardening, can you
Yes.
also predict fatigue failure?
Yes, cycling loading and fatigue failure. Yeah. It can do fatigue, it can do creep, it can do, well, stress and curve, it can do, yeah. Yes.
You have a question?
Yes.
I know nothing whatsoever about blue gene. Is it single precision, double precision? Is it mainly integer? What sort of?
I don't know. This I don't know. I don't know. We just run it on the blue gene and.
Yeah, but is your code, is your C++ code single precision flow, double precision flow?
It's okay. It's a mixture of both.
Thank you.
It's a mixture of both. Yeah. There is double precision and single precision. Yeah.
Another question?
No, thank you, Mr. Mayor. Thank you very much.